Hello there and welcome to our modules on probability concepts. My name's John Bone and I'm going to be your guide through these areas. So let's have a look at our first slides. And our first learning outcome statement here asks us to define a variable, an outcome and an event. So a random variable is simply any act that has an uncertain value. Let's take rolling a dice. Now, in advance of rolling that dice, you do not know what the outcome will be. So the outcome of rolling a dice is a random variable. Now, the outcome itself is the realization of a random variable. So if you roll a dice, what actually came up? So of course, the outcomes when you roll a dice are, and let's assume a fair six-sided dice. There's a chance of getting a 1, 2, 3, 4, 5, or 6. Now, the event is a set of one or more outcomes. Okay. So in other words, when we roll a dice, the total event is we could get a 1, 2, 3, 4, 5, or 6. Okay. So we turn to our next LOS, which is identify the properties of probability. And first one's up, we've got mutual exclusivity and exhaustive. Now, if events are mutually exclusive, it means they cannot both happen simultaneously. Now, when you roll a dice, the outcomes are mutually exclusive. You can't roll a dice and get a 1 and a 6 simultaneously. You will get 1, 2, 3, 4, 5, or 6. Okay, but you can't get two things occurring at the same time. So rolling a dice is a set of mutually exclusive events. Now, exhaustive means your set of events includes all possible outcomes. So when we look at our dice, we could roll and get a 1, a 2, a 3, a 4, a 5, and a 6. And that is exhaustive. There is no possible other outcome we can get from a six-sided dice. So we talk about that, therefore, being as the exhaustive set of events includes all outcomes. Now, let's have a look at the probability of an event. So the probability of event I, okay, is between 0 and 1. Now, what we're simply saying here is if we give the probability of an event a value of 0, we're saying it is never going to happen. And if we give the probability of an event a value of 1, we're saying it's going to happen 100% of the time. So the probability of an event being 0.5 would mean that we suspect it will occur 50% of the time. So probabilities of an event need to be between 0 and 1. What is the probability of rolling a dice and getting a 6? Well, okay, there are 6 numbers. And if we want a 6, we've got a 1 in 6 chance of getting that 6. So 1 divided by 6, and that gives us 0.167, or if you like, 16.7%. Now, for a set of events that are mutually exclusive and exhaustive, and remember our dice rolling remember the outcomes could be 1, 2, 3, 4, 5, and 6. And remember, we're assuming a fair dice, so each outcome has the same probability of occurring in this case. So each outcome has a 16.7% chance of occurring. Okay, if we add up those probabilities, and of course I have rounded here. In reality, it's 16.66666 recurring. I've rounded to 16.7. But if I didn't round and then I sum those up, of course, I will get 100% because I'm looking at all potential outcomes. So for a set of events that are mutually exclusive, so only one result can occur at a time, and exhaustive, we factored in all potential results or outcomes, then the sum of the probabilities has to equal 1 or 100%. So we then look at some types of probability, and we're asked to define empirical, subjective, and a priori. So let's start with empirical. Now, I might want to know what is the probability of rolling a 6. And let's say I know nothing about that dice. Let's say then I roll the dice 200 times, and then I count up the number of 6s, okay? And then I look at number of 6s over total rolls. And that, of course, gives me the probability empirically. So it's based on the analysis of data. I've used test data. I rolled that dice 200 times and I looked at the number of 6s I got in order to calculate my empirical probability. So it's based on test data. Now, a priori is based on reasoning rather than actual using test data. Again, I know with a fair dice, each outcome has the same probability of occurring. So therefore, I know the probability of getting a 6 is 1 out of 6 events, or 1 out of 6 outcomes, I should say, 0.167 or 16.7%. So that, of course, is a priori. I haven't actually rolled the dice. I am using reasoning and judgment. Now, both these two together, okay, so empirical and priori are often referred to be objective. Objective probabilities. Because I'm either using test data or I'm using rational reasoning. Now, what is not objective is subjective. This is based on my personal perception. So you might ask me, what is the probability of rolling a dice and getting a 6? And I say, I think 20%. Why? Because I feel that I'm a lucky person. Okay. Now that's purely subjective. That's purely based on my personal perception. Okay. So no science coming into it, no analysis of past data, no reasoning and experience coming in. It's just my personal perception. Right, with this little LOS here, we're asked to describe the probability of an event in terms of odds for and odds against. Now, we've been told the probability that a horse will win a race, because of course we see odds for events occurring at bookies, okay? And we've been told the probability that our horse will win the race is 12.5%, and we want to compute that as odds for and odds against. Well, if you want to compute it as odds for, you look at the probability of the event occurring over the probability that the event will not occur. Okay, so the probability that the horse will win the race is 0.125 or 12.5%. So therefore, the probability that it will not win the race is 1 minus 0.125, in other words, 87.5%. So we're taking 12.5% over 87.5%. Now, again, I think this is confusing to see how do we get to the 1/7 here, because if you do 0.125 divided by 0.875, then you get 0.1428, but we've written 1 in 7. Okay, well, 1 divided by 7 is 0.1428, but 0.125, okay, as a fraction is, of course, 1/8. So actually what we're doing in this computation is 1/8 divided by 7/8. Okay, so of course the 8s will cancel against each other and we're left with 1/7. So we've got a 1 to 7 chance that our horse will win. What does this mean? If you ran 8 horse races with this horse in it, okay, all equal horse races. So if you ran the horse race 8 times, our horse would be expected to win it in one of those 8 races. Okay. So in other words, we're expected to win 1 time and lose 7 times out of 8 races. Again, if you take the number 8 and multiply by 1.25, okay, so if we take 8, multiply by 0.125, we get 1. So we're expected to win 1 out of 8 races. So that's odds for. Actually, I think odds against are a little bit simpler. Okay, and this is actually the computation I tend to do. What we're going to do now is look at the probability of not winning the race divided by the probability of winning the race. So, of course, the probability of not winning the race is our 0.875 that we had before. So this time we're doing 0.875 divided by 0.125, and that gives us 7. So a 7 to 1. Now again, it means if this horse race was run 8 times, we would fail to win it 7 times and we would win it only once. Now, of course, you can see when we're looking at our odds for and odds against that they are merely reciprocals of one another. So I tended to find in my exam it was easier to calculate odds against, and if the question asked me odds for, just to flip my equation over. Okay, so now you can work out odds for and against an event occurring. Now we need to look at, and we move on to LOSD, which asks us to demonstrate or calculate and interpret conditional probabilities. So we need to talk about what an unconditional probability is, now an unconditional probability also goes by the name of a marginal probability. And we need to look at a conditional probability. And an alternative name for conditional probability is likelihood. Now, unconditional probability is simply the probability of an event occurring, ignoring any other events. So the probability that the stock market will be up for the day. But we're going to ignore any other events, such as the probability that interest rates rise during the day, probability of some big crisis occurring, etc. So an unconditional probability is simply the probability that an event will occur, ignoring all others. Now, a conditional probability. Now, here's the important one. And remember, our LOS says calculate and interpret conditional probabilities. So a conditional probability, note that it's given by P, A stroke B. Now, we need to be able to interpret this. It's the probability of event A occurring given that B has occurred. Okay, so probability of A, and here's our key words, given that B has already occurred. So the probability of event A, given that B has already occurred. So probability that our stock market is up for the day, given that interest rates rose in on that day. Okay, so remember, unconditional probability excludes the probabilities of any other events. So ignores the fact that interest rates could have risen or fallen during the day and just says what is the probability that the market will be up for the day. Conditional probability, though, is the probability of an event occurring given that another event has already occurred. The probability that the market will be up for the day given that interest rates rose. Okay, so we now move into looking at some rules, and we need to demonstrate the application of multiplication and addition rules according to our LOS. So here is our addition rule. This is the probability of event A or B occurring. Okay, so when it's written like that, it means the probability of either event A or B occurs. So we take the unconditional probability of event A occurring plus the unconditional probability of event B occurring, and then we subtract the joint probability. Here's our joint probability. And that's the probability of both A and B occurring simultaneously. Okay, and we subtract that joint probability, otherwise we get essentially a double counting effect. So imagine A was the probability that somebody drinks, B is the probability that somebody smokes. And we want to know what is the probability that somebody either smokes or drinks. Well, we take the probability that somebody's a drinker plus the probability that someone's a smoker, and then we subtract the joint probability, which is the probability that somebody both smokes and drinks. And we subtract that in order to avoid a double counting. And that's our addition rule. And we'll see some examples in just a while. We then turn to our multiplication rule. Now, this is our joint probability, the probability that A and B occur. So remember, this is a joint probability. And we're going to take the conditional probability, the probability that event A occurs given that B has already occurred, times the unconditional probability that event B occurs. And what is a joint probability? Well, it's the probability that both event A and a B both happen at the same time. So take your conditional probability of event A occurring given that B has occurred, and multiply by the unconditional probability that event B occurs. Okay, now it's nice because that means actually taking joint probabilities, we can work back to conditional probabilities. Okay, so if I wanted the conditional probability of event A occurring given that B has already occurred, and I've been given their joint probabilities, what I'd need to do is take their joint probabilities, probability of A, B, okay, no line between them, means a joint probability, and divide it through by the probability of event B occurring. In other words, simply rearranging the formula that we've got on our page. So we can, if we've got 2 out of the 3, in other words, if we've got a joint probability and a unconditional probability, we can work out the conditional probability, or of course, Also, if I had a conditional probability and a joint probability, then I could work out the unconditional probability. Now, the total probability rule, this is just the unconditional probability of an event occurring. And notice it is the sum of all of the joint probabilities that that event will occur. So the probability that event A will occur given that event B occurs, probability that event will occur given that event BC occurs, times the probability of event BC occurring. So just be aware, the unconditional probability of an event occurring is the sum of all of the joint probabilities. That's all the total probability rule tells us. Okay, now that's all well and good, but we haven't seen any numbers yet. So let's get into some examples here. So here's an example of our multiplication rule. The probability that both events, i.e. a joint probability, will occur is the joint probability. Now we've been given the probability that interest rates will increase, okay, and it's an unconditional probability, so it's not dependent on anything else. And we're saying there's a 40% chance interest rates will rise, okay, and therefore a 60% chance that they won't. The probability of a recession given the interest rate increase, okay, there's that word, given that. So we are looking at a conditional probability. The probability of a recession given that an interest rate has increased, and that's 70%. Okay, so we can say the probability of a recession and an interest rate increase. We'll take the conditional probability of 70%, multiply by the unconditional probability of 40%, and we've got a 28% chance of both a recession and an increase in rates. That's all well and good. I like to do them by looking at decision trees. So I'm going to just draw this up for you. Okay, so our first event is the unconditional probability. We always look at the unconditional probability first, and we're going to say there is a 40% chance that interest rates will rise, and therefore a 60% chance of no interest rate rise. We are then told that given that interest rates have risen, there is a 70% chance of a recession. So now we're looking at recession and no recession. So 70% chance interest rates rise and there's a recession. So there must be 30% chance that interest rates rise and there is no recession because they have to add up to 1. Okay, notice these add up to 1 as well. 0.7 plus 0.3 equals 1. So what is the probability of interest rates rising and a recession? We just multiply along our tree. 0.4 times 0.7, and that gives us 0.28, which is our joint probability. So we've got an unconditional probability, we've got conditional probabilities, and we've got our joint probability all showing up on a decision tree. Now, of course, we weren't asked in this question, but we could calculate it. What is the joint probability of an interest rate rise and no recession? That would be 0.4 times 0.3. So we would get 0.12. Now, we can use this to demonstrate the total probability rule. Total probability rule, if we take those joint probabilities and add them together, we will get the probability of the interest rate rise. So let's just sum these together. 0.28 plus 0.12 gives us 0.4, which is the unconditional probability of an interest rate rise. So the sum of the joint probabilities gives you, in this case, the unconditional probability. And of course, we've calculated those joint probabilities by taking the unconditional probability multiplied by the conditional probabilities. Lovely and straightforward. Okay, so I think it's quite useful whilst you're getting to grips with probabilities to sketch them out and label it up. It makes it a lot easier. Certainly will do when we start to look at things like Bayes' theorem a little later. Okay, so let's return to our slides. Okay, so here we are back on our slide. So the probability of a recession and an interest rate increase, as we said, the joint probability was 28%, which we saw in our diagram. Okay, so notice what we're looking at is the probability that at least one of our two events will occur. This is the probability of event A or B occurring. And remember, we already said it's the probability of event A occurring plus the probability of event B occurring minus the joint probability of them both occurring simultaneously. Okay, so again, we're subtracting that joint probability so we don't double count. And you can see we've demonstrated this here with a Venn diagram. So, going back to our example here, we've got a probability of rising interest rates being 40%. The probability of a recession is 34%. And the joint probability of both a rising interest rates and a recession is 28%. So what is the probability of either rising interest rates or a recession? Well, okay, we can do it by taking our 40% plus our 34% and then deducting our 28%. So there's a 46% that either will see a recession or interest rates rising. Let's go back to our decision tree just to label it up and make sure we're totally comfortable with this. Now, we're told here there is a 34% chance of a recession. Okay, now there was a 28% chance here of a recession and an interest rate rise. Overall, there's a 34% chance of a recession. So remember, we now need to look at no interest rate rise and a recession, or no recession. So if we had a 34% chance of witnessing a recession, there's 28% chance of an interest rate rise and a recession, and therefore there must be a 6% chance of a recession and no interest rate rise. In other words, this joint probability has to equal 0.06. Because when we combine them, okay, they need to add up to 34%, the chance of witnessing a recession. Now, again, using our total probability rule, we know that these have to add up to 0.6. Why do we need to know that they add up to 0.6? The sum of all of the joint probabilities has to add up to 100%. And if there's a 40% chance, we've got the 40% chance of an interest rate rise and a 60% chance of no interest rate rise, then these two probabilities, these two joint probabilities, when we sum them, also has to equal 0.6, the unconditional probability of no interest rate rising. Okay, so we can see we've now got a completed diagram that shows us essentially that there's a 6% chance of a recession and no interest rate rise, and a 54% chance of no recession and no interest rate rise. Okay, last thing we could do actually is calculate our conditional probabilities. What is the probability of a recession given no interest rate rise? Well, remember, the probability of no interest rate rise was 60%. We need to get to 0.06, so it must be a 10% chance of a recession given no interest rate rise, and therefore a 90% chance of no recession given no interest rate rise. We've fully labelled up our decision tree now, and I think these are really useful. Again, notice these events also add up to 1. If you take all of your joint probabilities, this, and this, it also adds up to 1, or 100%, of course. So using decision trees is a really easy way of dealing with your probabilities. Okay, it's a nice, easy way of dealing with probability questions. Visualizes the data, you label the data. Remember, you've got the first set of events in our decision tree is always the unconditional probability. The second set of events here is the conditional probability, in this case, chance of recession or no recession, given that interest rates had risen, or given that interest rates had not risen, our conditional probabilities. And then finally, take your conditional probabilities multiplied by your unconditional probability, and you get the joint probability, the probability of both events occurring at the same time. In other words, 0.28, probability of an interest rate rise and a recession. 0.12, probability of an interest rate rise but no recession. 0.06, probability of no interest rate rise and a recession. And finally, 0.54, probability of an interest rate rise and no recession. Okay. Lovely. Fantastic stuff. Let's head back to our slides. Okay, so essentially here we're looking at our addition rules. So we took the unconditional probability of a recession, okay, plus the unconditional probability of an interest rate rise, and then we subtracted the joint probabilities, the probabilities that they occur together. So 0.34 plus 40% minus the joint probability of 28% to get a 46% chance. There is a 46% chance of witnessing either a recession or an interest rate rise. Okay, for mutually exclusive events, this means essentially the two events can't simultaneously occur. That means the joint probability is always 0. So therefore, the probability of event A or B occurring, either A or B occurring, is simply the unconditional probabilities of both events occurring. Okay, so joint probability equals 0 for mutually exclusive events. Okay, final one, joint probability of independent events. What is the probability of rolling 3 4s in one toss of 3 dice? Okay, so each dice has a 1 in 6 chance of getting a 4. Okay, so probability of getting a 4 on one dice is 1 in 6. So if we want to know the probability of getting 3 4s when we roll 3 dice, it's 1/6 times 1/6 times 1/6. In other words, 1/6 to the power of 3, which gives us 0.00463. Okay, or if you like to convert that into percentages, and there's no reason why we shouldn't, our percentage is 0.463%. Lovely, and that is the end of this module.